on the website and on the social media. The 2 first e-seminars should already be available. Of course, you must agree on that. We already have the agreement of the speakers, but for all participants, if you don't agree, just write it on the chat.
Okay. Okay, so yeah, as Brunella said, this is the third FruitCREWS seminars, and we are welcome to introduce the speakers for today. My name is Rafael. I'm from the University of Bologna, and I'm doing a period abroad in Sevilla, in the group of Virginia and Antonio Diaz. And the speakers will be Riccardo Mazzoleni and Stefano Gianessi. Riccardo, he's currently a PhD candidate in the agricultural hydraulics and watershed protection at the Department of Agricultural and Food Science at the University of Bologna. His research focuses on water resources management related to the physiology of grapevine and other fruit plants, and the application of new technologies in precision agriculture and viticulture. The ongoing project he's in charge of is related to a new non-invasive soil moisture estimation technology called cosmic ray neutron sensing, CRNS. And Stefano Gianessi, he's graduated in geology and land management from the Department of Biological, Geological, and Environmental Science at the University of Bologna. During his research fellowship at the Department of Agriculture and Food Sciences, he gained experience in the calibration and validation of innovative sensors for the estimation of soil moisture over large areas. Currently, he works as an on-field technician at Finapp, and where he has completed multiple installations of CRNS probes for agricultural and environmental monitoring. So yeah, we're very pleased to introduce you and to receive your speaks. And yeah, the time is yours. Riccardo, you're first, and then Stefano.
Thank you, Rafael. Thank you for the great introduction, and good morning to everyone. I'll share the screen now. So hope everyone can see it. If not, just interrupt me anytime. Okay, so here we go. As anticipated, so the presentation title is on the use of cosmic ray neutron sensing CRNS in vineyards. Let's start with a brief outline. So what we're going through the presentation today. I'd like to, oh, sorry. Okay. So it's a bit late, the changing of slide. Anyway, what I was saying, yes, brief outline about what we're going through today. So we start about a brief introduction of what is soil moisture measurements and why it's so important in our applications. And then the focus on what is the cosmic ray neutron sensing technology and what is the usage that we are proposing now in agricultural fields. Then we go through the description of activities and the trials that we made just last season, as last season was the first year of experimentation. So I will point out some first results out of the trials. and then we'll see what are the still open questions and what we were able to reach out over the last year of experimentation. So let's start. So why is important soil moisture for us, and the context in which we are operating in the climate change effects on agricultural environments are more and more connected with its impact on water productivity and water balance. In this case, soil moisture is very important in controlling the energy fluxes in what's so-called the continuum of soil, vegetation, and atmosphere. And as a consequence, it can affect the atmospheric processes, including, for example, precipitation patterns and air temperature and evaporation as well, evapotranspiration as well. It could be important for as a proxy for our plants' water status. In fact, the plant's growth is strictly linked with soil moisture content, as this water is not only needed for the evapotranspiration, but also controls the mobilization of nutrients availability. And finally, manage water resources, as the accurate monitoring of soil moisture status is somehow essential for managing agricultural water resources. And the continuous monitor of the soil moisture status can help, for example, anticipating the plant's water stress and the possible onset of drought condition. There are many methods that estimate soil moisture, and basically are based on measurement of more easily measurable signal, I would say. These methods are often classified and distinguished based on some of their spatial and temporal characteristics, what we call scales, as for example in this image is visible how we can distinguish between sensors that investigate invasive point scale measurements or proximal sensing at the intermediate scale, or remote satellite scale at large scale. The traditional, I would say, soil moisture assessment techniques as a point scale invasive measurements, there are probably more widespread and used in these days, or one of the most used, may provide only isolated measurements of points and may lack of representativeness for a larger area. And what it needed usually is more dense grids of sensors that may be impacting on economical way. On the other hand, the satellite remote sensing is currently having some difficulties, I would say, with the issues such as small penetration depth in the soil and low overpass frequencies. So soil moisture could be acquired only for the topsoil, a few centimeters in the surface. Ultimately, in the last years, research emphasized the need of more integrated sensor that could aggregate data over field scale, and those sensors are represented by the so-called proximal sensing, so intermediate scale. And that's where our technology CRNS, cosmic ray neutron sensing, belongs. So is let's say, I would say, that bridges the gap between the point scale and the remote satellite sensing. So what the CRNS is, this technology relies on the inverse correlation between neutrons generated by cosmic ray fluxes and the existence of hydrogen, which is primarily present in the soil as water. The neutrons are coming from the atmosphere. They are naturally populating our atmosphere. It's estimated that in the palm of our hand, every second they come and pass 3 at second, let's say. The neutrons, these particles, are initially high energy and fast neutrons, are arriving in the ground, in our soils, and interact with hydrogen. And by this interaction, they lose energy and slow down. And the interaction, as I said, as anticipated, is mostly governed by the neutron-hydrogen interaction. The portion of this neutron energy in which we are more interested in is the blue one here in the graph, the what's so-called epithermal fast neutrons, which is the energy spectrum which is water sensitive. And because neutrons are generated and moderated in the ground and are scattered back in the air, this makes these estimation for our detectors to be suitable for non-invasive measurements above the ground. So that's the first important characteristic of the technology, is that the detector is a non-invasive measurement and it can estimate soil moisture over a large footprint. We can estimate about 5 hectares and also in depth into the soil of about 30 until 50 centimeters. I'd like to stress a little bit more the concept of the neutrons that are not really, let's say, interested or interacting with the soil matters as soil pedogenesis, as it is visible in this graph. This graph says that basically those epithermal neutrons flux is higher on drier soils, which makes the relation between neutron counts and soil moisture to be an inverse relation. And this relation, as I said, is not dependent very much on soil pedogenesis as it is visible from this graph. Okay, so next slide is to introduce a little bit more the context in which we are operating for our trials. So we are in context of what is called now precision agriculture and precision viticulture especially, and as a merge and as an approach to looking for optimized vineyard and agricultural operation management. Vineyard in particular operation are affected by water management, especially in regions like our Mediterranean regions, where water availability can significantly affect grape composition, grape quality, and yield at the end of the season. The relationship between soil moisture and grapevine is a, sorry. Understanding this relation. So understanding the relationship between the soil moisture and our signal of CRNS could provide a continuous and non-invasive value over a large area. And this goes directly to the objective of our study. And the objective of our study is to examine and assess the potential of this technology, the cosmic ray neutron sensing, to monitor soil moisture over a large area and the effect that soil moisture has on grape physiology. This is our site description. The site description, we are in a vineyard, not so far from Bologna area, is located in Imola, is about 40 kilometers away from Bologna. and is a vineyard which is managed by a private company. It's a Società Agricola Caci. The private company manages also the irrigation strategy and irrigation plantings. So is characteristics is peculiar because it's a subsurface drip irrigation over the 4 sectors that you can see from the image. We have installed a CRNS probe from Finapp, which is Italian-based company that former colleague Stefano will describe better than me after this presentation. And the total area of the vineyard is about 15 hectares, but as I anticipated, the estimated footprint area of the CRNS is more reliable, over 5 or a little bit more hectares. So our trial area is approximately 7 hectares. The vineyard is divided and cultivated with the 2 local grapevine varieties, which are Grechetto Gentile in light green or Pignoletto, which is PG, in this scheme, and the yellow one in the map is Trebbiano Romagnolo and Thiers. Before starting the activities and over these 4 sectors, which are northwest, northeast, southeast, and southwest, were selected randomly 80 vines. So the CRNS comes to these activities. So first we installed the probe, as in the picture. This is a Finapp probe that, as I said, Stefano will talk about later on. And we wanted to also map the possible heterogeneity within the large area that we are considering. So for that, we used a portable time domain reflectometry instrument from Spectrum. And then concerning the plant's physiology, we made some measurements related to vine water potential with stem water potential, and we carried out some grapes quality analysis in the lab at harvest. So CRNS, independently from which probe you're using, come to the necessity of calibration after the installation. So here in the picture on the left is visible our installation of the Finapp probe. Here's a zoom of the detector inside with the battery, which is powered by the solar panel. As you can see, is a very non-invasive installation. All the field operations are easily carried out during the season. So as concerning the the calibration, it consisted to acquiring soil samples over the trial area. The soil samples were locations were identified by some points, as you can see. Every point in total are 18 points, every 60-degree angles at a distance from the sensor of 3, 35, and 120 meters. In each location, we took samples at 4 different depths for the detection of more accurate spatial variability. In total, there were 72 samples for lab analysis, and after the lab analysis, it was possible to end up with these parameters. So the parameters that we needed were gravimetric soil moisture on that day, the bulk density, and the soil organic carbon and lattice water. So those parameters are important for the slide that comes next, which is the equation that we use for after calibration to convert the neutron counts into soil moisture. So as I anticipated, the relation is inverse, and in this way, neutron counts can be transformed into volumetric soil moisture. So these are all the parameters that I previously mentioned. So the static hydrogen pools, as for lattice, water, and soil organic carbon, as well as the bulk density and water density. And a little specification is about the NC parameter. The NC and neutron counts are corrected for air pressure, incoming neutron flux, and also air vapor. So now I want to show you a little bit of first results by starting with our TDR campaigns, with the portable TDR. The TDR acquisition were based on a grid of points of 50 meters per 50 meters. And in each point we acquired 5 measurements with the portable TDR. This operation allowed us to end up with these 3 heterogeneity soil moisture map over 3 dates. 2 of the dates were carried out at the beginning of the season, at the very first one at the beginning of May, the second at the end of May. And as we will see in a moment, May was kind of a tough period with precipitation in our region. So that's also why the soil moisture values appear to be a little bit high in this time, in this moment of the season. And the last acquisition was at the very end of the growing season, 1 month after harvest. That was made to check if the heterogeneity that we could see was somehow confirmed. And as we see, we have the eastern part of our trial area, which is a bit more, let's say, humid than the western part. So we now show you the CRNS response to the precipitations and irrigation events that we had in the last season. The time frame goes from the 1st of April until the 31st of October. So as I anticipated, the May period was kind of tough with the precipitation. We have 2 big rain events in May, but then the precipitation pattern went a bit down, and as it more frequent in these years along the summer, it basically never rained. But the signal of the sensor responded very well to the precipitation events, and also I highlighted the irrigation event. I want to specify that the irrigation event in this graph is not millimeter per day, but it's just to emphasize the day in which an irrigation took place. And again, in this period, we are pretty satisfied with the pattern, with the dynamic of the soil moisture of our sensor. I continue with some results, preliminary results on the water potential and quality parameters at harvest. So you can see the Pignoletto results on the left part of the screen in green, and in yellow the Trebbiano Romagnolo features. So we done concerning the stem water potential, we tried to talk acquisition of stem water potential before and after irrigation. We've done it 3 times along the season. There are no big differences in terms of statistic. The only one little evidence is that in the western part, as anticipated from the TDR maps, is a little less humid than in the eastern part, and that's visible for our Pignoletto stem water potential. In the date of 3 August is a little bit more stressed than in the other dates, but usually along the season the vines did not experience much water stress because the irrigation planning was kind of strict, carried out from June to end of August and also the beginning of September. And also concerning the quality parameters, there are no big difference in terms of sectors and varieties. As the enological, let's say, enological goals, the harvest was made a little bit earlier than the normal because the grapes were destined to producing sparkling wine. So for sparkling wines, we needed to have a more acidic content. So that's why the harvest was carried out a bit earlier rather than normal. I will conclude with some points that we treated along the presentation. So we saw how the CRNS is operating and how the technology works and how possible application is in agriculture and especially in this case in vineyards to monitor the soil moisture over field scale area. There are still open questions on the research and the research concerning the CRNS, which is how plants water demand, for example, and how to interpret the CRNS data and concerning also and linking also the plant's physiology response. And also the final aim and the final open question would be how to modulate irrigation and to plan irrigation based on the CRNS signal. With this, I conclude my presentation. I would like to thank you very much for your attention and thank you also to all the people that participated and helped me at contributing to this experimentation for the first year. Thank you.
Thank you, Riccardo. And now we will leave the questions for later. Now we will have Stefano's presentation, and then we will do the round of questions and answers.
Thank you, Raphael. Do you hear me good?
Yes.
And thank you, Riccardo, for your presentation. And I really enjoyed even the last picture you made of the field because it feels very big, the vineyard. Very nice picture. I will ask you to share it with us. Yes, so hello everybody. My name is Stefano Gianessi, and as Raphael introduced, I'm working in field, installing and calibrating CRNS probes, and in the presentation, I will show you some application that we derived from the soil moisture signal that we acquire. So we will have a little introduction about Finapp, where it come from, and what is why is there we are introducing some innovation into the soil moisture monitoring environment. We will look some static application, and finally a Finapp DSS for irrigation, so decisional support system for farmers and for agricultural operators. And I will show you, I will give you an introduction for the using CRNS technology to map soil moisture variability. So not anymore a static application, but a mobile application. So Finapp is a company born as a startup in the physics department of the University of Padova. And we produce soil moisture sensors or soil moisture probes, we like to say, with the aim of adding more value to the resource of water and to the agronomic activities. So as you can see, the probe on the left is installed on a pole with no contact with the soil. It has his solar panel and a small battery and a detector inside. That counts over time neutron particles colliding the detector. So Riccardo introduced a little bit the physics behind the technology. So neutron fluxes coming from the universe will hit the surface of the Earth and interacting with soil moisture. The soil for up to 50 centimeters deep into the soil and traveling horizontally for 100 of meters before reaching the probe and count and the probe will count the event. So what we do is that we measure water on the large scale of 5 hectares. This is because the particle can travel hundreds of meters before reaching our detector, and in depth because it can penetrate for 50 centimeters the soil. We do application for agriculture, for environmental monitoring, because we can, with the same technology and different configuration, we can measure water in the snow, for example, which is a parameter interesting for a lot of environmental situation and technologies there in that field have some limitations. So the need of a new technology and a need of an aerial measurement and not anymore a point measurement was needed, as in agriculture, I would say. And yes, so this is the scheme I was telling you before. The cosmic ray in the orange arrows collide with hydrogen, get thermalized, so they lose energy due to the collision with hydrogen atoms, and eventually comes out and hit our probe. So high number of collisions of neutron counts underline a situation of low soil moisture in the soil, because the attenuation will be less, so there will be more neutrons, and vice versa. When the soil is wet, this collision produce interact with hydrogen and will stack the neutron inside the soil, and we will not count it. So low number of neutrons, high humidity, high count of neutrons, and the dry soil. This monitored in real time and continuous will give us the dynamic of soil moisture in time of such a big area. So Finapp has patented his inventions and which is completely new with other CRNS producers, because CRNS technology is well known since many years, like 40 to 50 years. But producers used different technologies than us. They used proportional gas tubes to count the interaction of molecules of cosmic rays with gas in tubes. We switched, thanks to innovation in technology, we built a probe that counts thanks to a plastic material and a photoscintillator. So here inside the probe we have some lithium foils and some plastic sheets that emphasize the collision and the spark of lithium when a neutron collides to the detector. By using this technology, the gas tube were obsolete, so we could reduce costs a lot and dimensions a lot, and this opened a completely new era of application and clients also. So we are working a lot with farming and a lot with monitoring environmental agencies. This slide is just to stress a little bit the advantages of this type of system for monitoring soil moisture. We don't have anymore a point scale probe, but we have an aerial measurement of volumetric water content. And because it is not in contact with the soil, this technology can be adapted to any type of soil, even to soil with a lot of stones in it, where the use of point invasive scale measurement is hard because you lose cohesion from the sensor to the soil, and it's really hard to have an idea of the soil moisture dynamic in these type of soils. And even the plant on soils doesn't affect the measurement. Maybe a very bushy plant can lower a little bit the statistics of our count rate per hour, because as we know, plants are made of water. There is a portion of water into the plants, but this is interesting because there is the possibility to estimate even how much water is in the soil and in the plant. So following even a trend of soil moisture, but even a trend of biomass water content in the plant. This theme is a little bit ongoing process in development, and for sure a lot of effort will be put in the biomass water equivalent estimation. It is indeed an easy installation on the pole, and even maintenance is almost zero. The maintenance of this probe is at least maximum, like changing the battery, a 7 ampere battery, when there is not enough sunlight to recharge the battery. And the durability of the probe is potential can be almost 10 years or even more. So thanks to this new technology, we have a new measure, and today I will show you a little bit presentation of what we are doing with this measure, that is giving irrigation advices. So this is a field in Trentino, in Val di Non. It is an orchard, apple orchard. We are in a valley, in a big valley, but we are on the hills, like 1,500 meters on the sea level. The geological nature of the soil is glacial, so we have a lot of stones inside the soil, and the depth of soil has a big variability, ranging from 20 centimeters to 70 centimeters. So even the modeling of soil moisture in such areas can be difficult, and classic traditional sensors were hard to interpret. So we installed a CRNS probe where we recorded along the entire season, and we can see that we have a recording during all the entire year, and the fluctuation are well in agreement with precipitation. What we look by looking at this type of data is the fluctuation of soil moisture dynamics. Okay, the maximum and the lower end of the trend of soil moisture. I like to stress this because by looking at this data, we can figure out some lines, some values that are that correspond to the storage of my field. So this blue line in the scheme and the red line will be pointed as a field capacity and wilting point of my type of soil, and the range between these two limits will be the available water content of my stratum, of my continuum of soil. So having in mind this allows us to monitor soil moisture when it arrives into a critical situation. We know that there is the need of an irrigation. So this is the concept I was describing, and in order to define these parameters that are necessary for irrigation scheduling and irrigation monitoring, there are different methods to evaluate these. Some are analytical methods, so numerical models like pedotransfer functions to estimate this storage available of our soil. This works very good for known type of soils. So maybe there are a little different type of pedotransfer functions around the world. Each pedotransfer function works very well with a specific type of soil, I would say. And you need to have a lot of knowledge of your system in order to create such pedotransfer functions. Then we have some standard and tabular values that describes how much water holds a sandy soil or a clay soil or a mix between sandy clay soil. So there are not very site-specific rules. Then we have some measurement methods on the other hand, laboratory measurement such as the Richard plate. But here with this technology, we bring some innovation, and we can set these parameters just looking at the dynamics of the field, of the soil, putting a high field capacity when in very wet conditions, and a wilting point during very dry seasons. Obviously, this type of let's say knowledge leads to an irrigation support system for the farmer that allows to see the big picture of soil moisture of the entire field, and integrating it with meteo weather forecast for the days coming and the situation in the field at the moment is capable to give an advice of how much to irrigate and when to irrigate. So this is a very easy dashboard that the farmer can ask, can interrogate every time he wants to plan an irrigation or wants to have an advice. So we tested we tested our technology with an installation in Umbria, in central Italy, the center of Italy. And in the first year, in the 2022, we just provide the customer the soil moisture monitoring. So he was just we didn't have the DSS ready, so during the season he just watched the storage going from empty to low, the dynamics over time. Just this knowledge, having a big picture idea, really helped him in increasing his yield and the quality too. So not having any stress periods, or at least having it very soft, helped a lot the plants to grow better, and at the end of the year the results were quite good. And this year in 2023 we added a value of how much to irrigate. So we were giving an advice to the farmer, and during the season were 7 crucial periods of very low end soil moisture and no rainfall coming, and we suggested irrigation for every period that helped the plant to grow with no stop in the process, and that leads to a very big yield. In comparison, these values are all related to a comparison of our field that was about 2 hectares, and the entire portion of his fields that was like 70 hectares. So these numbers were related our parcel and respect to the entire plantation he has. And this year we arrived to a less irrigation, less water given, a lot because in the other parcels they are not having drip irrigation, but they are having sparkling irrigation or rainfall irrigation. So this irrigation data is a little bit tricky, but the difference was not noticeable. We know that the agricultural management is very complex. So this micro irrigation, drip irrigation was was managed in different management zones, and irrigation was set once at a time, so one sector per time. So when he was irrigating the upper north, the rest was not irrigated, and so we have this type of agenda, irrigating from north to south. Here we have our sensor, and we decided this position to be the better, that suits for us, because we didn't want that irrigation happening in other sectors would affect our areal soil moisture signal. So we liked it to put it very far down. But during the season, we see that we could see even the other irrigation. Okay, we can see that this peak is big rain, then we have a decrease, and then we see these peaks, 1, 2, 3, 4, and 5 peaks that are exactly the irrigation of the 5 uppermost sectors. So in order to have a DSS, a decisional support system that gives a number and when to give the irrigation to the farmer, I think it's crucial to have a key positioning of the probe, as we did, and how to schedule this irrigation in order that irrigation on the other sectors doesn't affect our measurement, or let's say in a better way, decide to irrigate the sector in which the probe is installed as first. So you start with irrigation from the sector where you have the probe, so it's not affected by nearby soil moisture, or at least the nearby soil moisture is the same in your field. So you start giving an advice, and you implement this up north to the rest of the sectors. So another complexity that we can find, and customers asked us how to take knowledge of it, is that maybe in the same field we have different age of plants. So the coefficient, the cultural coefficient of the plant could change a little bit, and how we could take care of it in our irrigation advice. An idea that came in mind to apply is that we can play with the coefficient, the cultural coefficient of the plant, because in our irrigation advice is a part of so coefficient is a part of our irrigation advice. In order to forecast soil moisture, we check soil moisture as recorded by the sensor, weather forecast, and the coefficient, the plant parameter, to forecast soil moisture in the tomorrow and to give the correct, the more correct advice. So maybe an older plant will be more stable, while a younger plant will need more, will ask for more water. So from one sensor, from one soil moisture measurement, we arrived to a differentiation of irrigation advice, let's say, more plant dependent. Lastly, we are doing multiple spatial variability tests, so measuring soil moisture even into a bigger scale. So mounting 2 probes on the tractor, moving inside the field, and acquiring soil moisture map variabilities along each path. There is a lot of interest in such application, because as we know, there are a lot of variable ratio machinery out there, starting from seeding to cropping and to irrigation systems that has this type of variable ratio. So having such prescription maps will really be implementing these machines. In this area, in this field, we found a good correlation in the center, because we know that it is usually a wetter area, because there is a drainage system to allow any ponds around. So this is the first comparison that we have, and then other high value of soil moisture or low value soil moisture need to be understand with the integration of multiple sensors or acquisitions, I would say. So this is again how the probe looks like, and internally we provide neutrons counts, muons counts, that is a particle directly proportional to solar activity and incoming of the cosmic ray particles, and pressure and temperature at the same time. And this is a configuration for agricultural purposes or environmental monitoring in a more sense, in a bigger sense. And this is the configuration for snow water equivalent estimation. As we said, with the same hardware and used in different type of configuration, we can reach multiple signals, and we can play a lot with it and try to extract really helpful and let's say genius or interesting products. So with this, I would conclude, and thank you a lot for the opportunity to be here. And yeah, very interested in answering to some questions if you have.
Yeah, thank you, Stefano. Thank you also, Ricardo, once again. And Artur Krakowski, I'm sorry if I'm pronouncing wrong, but you asked if the presentation would be available after the event. There will be a recording of the call, so you can share with your partners and your colleagues also. It will be available both on YouTube and also on LinkedIn, so you can share. So there was a question here also from Arthur about he says, like, it appears like a single point of measurement. How do you get the distribution over a large agricultural area? Maybe it's for both of you, if you can answer.
If you don't mind, Ricardo.
Sorry?
If you don't mind, I would answer to these questions.
Yeah, I don't. Please go ahead.
Yes, because it's true that you see one probe installed in a position, but you have to remember that what the probe is recording is counts over time, so collisions of particles into the detector. Okay, so our soil moisture is based on these counts over time, and there is a relationship between counts and soil moisture, as Riccardo showed. It is called a Desilets equation. And so we can link by a few free parameters neutron counts to soil moisture. And the footprint is such big, because neutrons have the ability to travel space 100 meters before reaching our probe, and can penetrate to 50 centimeters down to the soil. So the sum of our signal will come from such large area and such depth. It is a big volume in such sense.
So to understand well, you're doing the average of the soil moisture over the larger area. It's not for specific point in every house place on the field.
Exactly. It is indeed a big average of this portion. In order to have variability inside your field, you have to put these sensors into tractors and to move it, like to doing a mobile application. In this we are working a lot, because maybe you are not satisfied with just an average value, but you want more precise. And so the rover application is we are putting a lot of effort in it.
All right, it's good to know, because in fields which we are working with, there is a variability of the types of soil, and there is kind of water reservoir on the sides, and there are some irrigation tunnels around, and there are different ways of irrigating. So we need to know exactly what happens in every part of the field. Thank you.
Yeah, and for that case, definitely an integration between multiple technologies will be for sure the answer, I guess.
There is a question from Lotfi. Feel free to ask.
Yeah,
I think that the microphone is turned off.
or be closer, please, to the microphone.
No? It's okay?
Yes.
Okay.
Yes.
As you know, for the presentation, first of all, as you know, we are the service of farmer, and price for them is very interesting factor. It's necessary to know price of such instrument.
Maybe I would suggest to write down the question in the chat, because quality of the sound wasn't so good.
It's in the chat. It's just for the price, because you know we try to help small farmer to manage water, especially in the context of climate changes. Okay, no?
So Stefano, maybe it's for you. So he was asking about the price of the technology of the Finapp probe. I see now that he wrote also in the chat. So
yeah,
if you have any useful information for him, maybe Stefano.
I'm sorry to interrupt, but I think that maybe a personal contact. This is,
Yeah.
I'm sorry, this is not the, I'm sorry, no, lot fee, but this is not the time for like promoting
Okay.
products or
Just
telling the prices or, so I'm sorry to interrupt. Yeah. Brunella, do you have a question?
Yeah, I was also curious about the price actually, but anyway, if it is, you know, not, if they don't want to say it, it is okay. Yeah, or maybe just the range, I don't know. My other question, yeah, my other question was about small farms. Indeed, Lofty was referring to small farms, and I wonder whether, well, first is which is the minimum in the standing sensors, which is the minimum, let's say, surface that you can measure, and whether you are thinking to solutions for reducing the extension of your measurements, because most of the time in many European countries, farms tends to be very small. And so also the plots of the different crops might be quite small. So I wonder whether you are dealing with that, or if it is, you know, not possible to go under a certain surface of the orchard. Thanks. But anyway, very interesting presentations, both of them.
Thank you. Thank you for the answer.
Thank you.
So the footprint, there are some studies in reducing the footprint sensitivity of the sensor and reducing it from the 5 hectares that we are talking about today. But so far, I didn't see any application of it. Maybe there are different type of technologies, even non-invasive technologies that suits better with smaller fields, such as I've worked a lot with gamma ray spectrometry that has a smaller footprint. But as we like to see, we are working with the cosmic rays, and so the footprint is not a minus, but it's a plus. So we are into applying such technologies. And irrigation treatment to be the same. The costs are not like punctual probes because the lithium inside and the structure and the manufacture of the probe is slightly more complicated. So it goes around 5K, let's say. We have even some rent options, but for this, just to give you an idea of the cost that we provide.
Okay, thank you, Stefano. Is there any other question? Okay, I have a question actually. I would like to know, like, I have 2 questions. If it's possible to calibrate, the questions are both for both of you, this one. If it's possible to calibrate based on the point measurements you do closer to the root system. Because I was imagining, for example, apple orchard. Okay, you have the inter row and the rows with very different soil water content. So because the idea is like if you have 5 hectares of apple and you measure the 5 hectares, you might be underestimating the soil moisture content because you're measuring also the inter rows or 5 hectares of viticulture of wine or vineyard. You could be underestimating the soil water content, and then you would overestimate the irrigation necessity. Is it a problem, or is it possible to calibrate only on the raw soil moisture content?
Well, yes. Thanks for the question, Rafael. I'll start answering, and then Stefano maybe can help me out with some more information. So the problem, let's say, with calibration is exactly what you said, and that's why it is more accurate to have more than one calibration campaign along the years. So we pointed out how the sensor is suitable for long-term application. So if not in 1 year, maybe the next year or the next couple of years from the installation, it would be better to repeat the calibration campaign to see if there were some errors in the first campaigns or whatsoever. So that's first point. And maybe if there were some errors, they could be corrected over more campaigns of calibration. And that's what also you suggested to be the place of the actual soil sampling. So if within the interrow or in the row, that's another issue, but we can overcome this issue by selecting or choosing a date quite far from the irrigation time, or with the more, let's say, uniform soil moisture over the area. So we usually run out calibration in a moment of the season in which we don't have any irrigation interventions to do not end up with the situation in which under the plants there is a certain amount of soil moisture and in the interrow there is another completely one. In case of drip irrigation, it's usually the case. So in between the rows of plants, there is a different amount of volumetric soil moisture rather than under the plants where the drip irrigation is flowing. So yes. I would suggest to run calibration in a moment of the season in which we are not irrigating. And this could be a solution for this issue that you were suggesting.
Yes, and in order to better knowing what is the amount of soil moisture down the drip irrigation line, is because as you pointed, we are measuring a big volume, but we are irrigating just few rows, right? So we end up underestimating the soil moisture which is useful for the plant. In this case, I see a few options. One is that what we are doing is to ask to the farmer to report the amount of irrigated water and the date, so we can give an emphasis of the soil moisture signal in that moment, and saying that the emphasized signal is an underplant signal, let's say. Don't know if I'm explaining. And another option, as Riccardo suggested, is to point out some specific calibration. So maybe sample before and after an irrigation, and in somehow introduce this data into the soil moisture signal, and have an averaged soil moisture signal and a plant-based soil moisture signal line. And a third option I would see is to implement some point scale measurement like TDRs or phretimeters exactly in the down the drip irrigation line to have multiple information coming from different type of sensors, and in somehow to integrate these tools together. Yeah.
Okay. Yeah. As you said before, the integration of technologies would be better in this case of small properties, maybe. The other question was regarding the mobile application. Did you limit the range of action of the sensor, or it's still measuring 5 vectors in each point of measurement? I didn't get it.
So we are not decreasing the footprint because that is not physically possible, but we are moving. So we stay a few moments into a point, then we move. No, so the probe is has this such big footprint, but is 80% or 50% of the contribution of the signal is coming nearby the soil. So it's coming closer to the probe. You have to think of like a cone, a big cone of sensitivity, which is higher where the probe is installed and into the upper. And far you go and down you go, you have a little less probability that the neutron is coming from that lower and faster portion. So we believe that moving is like creating a pattern and looking and skipping at one moment at a time different the properties of the soil. So the contribution to my signal will come from an area that is 20 meters. There is still a lot of scientific debate on that, but I like to see it as a person where okay, I feel like to be in a wetter area and moving okay, but not looking but sensing.
Yeah, but what I didn't understand is like by changing the height of the probe, do you change the footprint or not?
No,
If
that
you put it close to the soil, wouldn't you restrict the footprint?
well, a little bit. I restrict it not from 5 hectares to 10 meters, obviously, but from 5 hectares to maybe a cell of 50 per 50 meters, let's say. This could be the approximate resolution of the roving technology.
Yeah, it's great. I think it's a very innovative technology and very useful for many applications. We are just used to fruit crops, which are maybe the hardest to apply the technology. But it's very, very interesting. Is there any other questions that maybe the participants might have? Well, I don't think so. So yeah, I would like to thank you again for the participation, for the presentation, and for sharing with us this technology and the advances that you were having. And we're hoping to reading your publications and your papers soon enough. Thank you very much.
We hope as well.
Yeah.
Thank you, Rafael, and thanks to all of you participating this afternoon.
Thank you very much.
Thank you all and
Thank
bye.
you, Brunella.
Thank you.
Have a good afternoon, everybody.
Okay.